open. Oh, are you all seeing, you're all seeing probably the smaller screen than the larger one, huh? Okay.
Now we see it in not presenter mode, in the correct mode.
Okay, great, great, great. Okay, so I was given the not so insignificant topic of talking about the link between air pollution and acute respiratory infectious diseases. I have walked the line between air pollution and infectious disease research for a long time now. Um, uh, Normally with respect to infectious disease spread and also with respect to development of chronic respiratory conditions like asthma, and find them to be entirely linked. And we're going to talk about this from the 10,000-foot view a little bit, but I hope it triggers some good ideas, some good comments, and some different research directions. Well, when we study respiratory infectious diseases, there are many risk modifiers, whether it comes to incidence or the occurrence of infectious disease, and also the severity of infectious disease. Some of these are shown here pictorially. From the upper left, we have age, and then going clockwise, population density, poverty, healthcare access, genetic background, including the genetics of the immune system, nutrition, exposure to tobacco smoke, presence of chronic conditions already like asthma, and then indoor and outdoor air pollution. So we have many ways that infectious disease spread can be modified within a population, and the severity can be increased or mitigated within an individual. And of course, this varies by infectious disease and according to some other modifiers not listed here. For today, of course, we're going to focus on the two risk modifiers, indoor and outdoor air pollution. For indoor, it includes things like burning of biomass, smoking. We could think about ventilation there. For outdoor air pollution, of course, vehicle exhaust, industrial, and anything else that can get particulates in the air, right? Dust storms. The link between air pollution and infectious diseases can be identified as early as the 1918 Spanish influenza pandemic, which of course was one of the most traumatic and horrific events that's ever happened in human history. Somewhere between 50 and 100 million people were killed, depending on the estimates you look at. This paper in particular looked at a couple different regression models, which I just simplified here to say model 1 and model 2. Just know that they have different confounders adjusted for them. And they looked at the difference in mortality during 1918 and the surrounding years between cities that had high coal usage versus low coal usage, and then medium coal versus low coal. And what you can see is there is a huge difference in the betas, or the contribution of coal usage to how much both infant and all age mortality that we experienced way back in 1918. There is evidence from studies around the world, everywhere from Guatemala to Italy to China, showing an increased risk of severe acute respiratory infections. I'm going to call those ARIs from here on out, and acute lower respiratory infections, ALRIs, which tend to be more significant, higher severity in both women and young children, where biomass is used for cooking and heating indoors. Of course, that's mitigated by ventilation level, but we also see it in the US. There are studies came out of Arizona. There's the Harvard Six Cities study, and many others that show the same thing as we see in other impoverished and wealthier nations, that ARI risk among children is higher if biomass is used for cooking and heating. So we have a strong connection already between indoor air pollution and these infectious disease outcomes. At the same time, we have good epidemiologic evidence, lots of papers showing associations between particulates and NO2, leading to increased risk of ARIs in children and in adults. The types of evidence we see is typically associations over time. I'll show an example of that in a moment. The most common types of studies focus on rhinovirus, which is of course the common cold, respiratory syncytial virus or RSV, which is one of the most common infectious agents known to mankind. Literally every person in the world is infected by the age of 2. Lots of studies with influenza and tuberculosis. So those are probably the 4 most commonly studied respiratory infections. Tuberculosis, of course, being bacterial, while the others are viral, but there are many others that have been studied in this way. It can be very difficult for those of you who have tried to do work like this. It's very difficult to test some of these associations in controlled ways or even in ecological ways, because you have collinearity of multiple risk factors. You have a lot of connection with temperature and humidity for both air pollution and respiratory infections. Poverty is a huge confounder, and it can be very difficult to tease out the cause and effect. Of course, as you all very, very well know, it's difficult to use stationary monitors to estimate actual individual exposure. So the use of personal monitoring is, of course, advancing our knowledge of air pollution exposure in many ways. But one of those ways is being able to monitor individual air pollution and track someone's respiratory infectious outcome. Here's just a quick example study of the types of things you see in the literature when people are looking at air pollution and respiratory infection. This is a temporal study trying to overlap AQI with ILI, ILI being influenza-like illness. It's a very common marker that's used to track winter seasonal respiratory infections. So we see a lot of studies using ILI, and they usually take a lag time between short-term air pollution events and then short-term changes in respiratory infectious disease outcomes. We also see a lot of use of long-term air pollution exposure relative to respiratory infectious disease outcomes, but I'll talk about that a little bit more in another example. Okay. I think it's really important to note how and why air pollution and respiratory pathogens are just inextricably linked. They are so closely tied together, beyond the fact that they're both just aerosolized, right? So the first is that both play an absolutely critical role in early pulmonary development. We know that respiratory syncytial virus, RSV infection early in life, if it leads to a more serious ALRI in childhood, we know that that's one of the key predictors of that child developing asthma later in life. About 20% of early childhood asthma is due to a serious RSV infection early in life. We also know that early exposure to air pollution during development, can predispose children to developing asthma and other chronic respiratory conditions. It can cause overall reduced lung capacity and lung functioning. So both play an absolutely critical role early in pulmonary development, from the time of conception through early childhood. At the same time, as I mentioned before, both respiratory pathogens and air pollution are influenced strongly by temperature and by relative humidity. So as temperature changes, as humidity changes, how the bioaerosols and aerosols behave can change pretty dramatically. Some respiratory pathogens, again, like RSV, have actually develop proteins on their surface that change shape and configuration in different temperatures, so that they can tell when they go from a cold outside air to a warm inside nasal passage, for example, and they can bind to cells. With particulates, of course, whether they stay suspended, whether they are pulled out of the air by humidity or precipitation really matters. I should also mention that both are and can be influenced by wind. Further, so if we want to talk about human populations and how both interact with the human ecology, they're both found more commonly in impoverished areas and population dense areas. So it's really important to note that both of these respiratory challengers, per se, are can also be tied to issues of environmental and social justice very readily. A lot of minority populations, impoverished populations suffer disproportionately from both. Both respiratory pathogens and air pollution activate an inflammatory immune response. So they promote antibodies. They can both be found connected with atopic allergic diseases. If you have an overactive, essentially, immune response. Both can damage the respiratory epithelium by triggering neutrophils as well as other mechanisms. And so if you have strong exposure or serious outcome from a respiratory pathogen or from air pollution, it can result in long-term lung damage that will predispose you to worse outcomes when you're exposed to them in the future. Both respiratory pathogens and air pollution trigger exacerbations of chronic respiratory illness like asthma and COPD. Of course, we see in children what we call the September asthma epidemic, where 17 days after the start of school, because rhinovirus starts circulating, you see this huge spike in children going to the emergency room due to asthma exacerbations. There's lots of evidence that spikes in air pollution also send children and older adults and people with chronic respiratory illnesses to the ER at higher rates. Okay. So now what I want to do is talk through several of the possible causal pathways that connect respiratory pathogens and air pollution to higher ARI incidence or worse outcomes. So again, we're lumping together here incidence of acute respiratory infection and severity. So whether people are more likely to be hospitalized or killed due to exposure, okay, or due to infection. So the first I wanted to talk about is one that's been hypothesized, but it's been very difficult to test and prove, mostly because of the limitations of the ecological data and analyses we have available to us that I already mentioned. But the first is that respiratory pathogens themselves may transmit more easily through polluted air. So when someone sneezes, coughs, talks, laughs, right? They're emitting droplets. Many of those droplets are heavy and fall to the ground. Many are light. They evaporate very quickly to a small size and are able to stay suspended in the air. There's the possibility that in a more polluted place, those droplets are able to kind of coalesce around around particulate matter and be carried farther and wider. So that's one that has been hypothesized. People have looked at it. Actually, I've tried to look at it, and we haven't proven one way or the other, but it would make sense from a mechanistic standpoint. The next one is that there is an interaction effect between air pollution and respiratory pathogens. So in the presence of both, if you're exposed, especially early on, then they can, in their combination, result in poor lung development or extensive lung damage, which leads to overall decreases in function and volume, especially in early development. And so it could be that the presence of both, and we know that the presence of both are higher again in impoverished areas, could cause far worse outcomes than either alone. The next is that we have exposure to air pollution during early development. So say infancy through early childhood, when the lungs are very rapidly developing. So there's exposure to particulates, NO2, leading to decreased lung function, doing damage to the lungs. And then when there's a respiratory pathogen that challenges or creates an inflammatory response, there's a much worse outcome. They're much more likely to show symptoms or have something develop like a viral or bacterial pneumonia. So in that case, it's air pollution first, pathogen second scenario. The next, so you can see I've switched out my little picture of lungs for an antibody as a representative of the immune system. In this scenario, exposure to air pollution, severe early respiratory infection, or a genetic predisposition leads to an increased inflammatory response. So I've covered a lot in that suggestion, because there is, of course, every time we're exposed to a respiratory pathogen or to air pollution, an inflammatory response that occurs, and the level at which it occurs depends on our genetic background. It also depends on what we've been exposed to in the past, and how our immune system developed, again, especially in early childhood. So these are really important during infancy, during that first year of your immune system really starting to develop in different ways, and including at what level inflammatory response you're going to have in the presence of challenge. So this can be an and or first, second, but just in the presence of everyone's individual immunogenic response. Here we have exposure to air pollution dampening the immune system first. So if someone's exposed to chronic air pollution, then their immune system simply can't respond as well. It's lessened. And so when there's a challenge or an infection from a respiratory pathogen, they have much worse outcomes because their immune system is just weakened by the presence of air pollution. Okay, so I wanted to say that aside from the first one, the hypothesized causal pathway here, there is good evidence in the literature for all of the others. So whether it's a combination effect of respiratory infection and air pollution, a before and after, dampening of the immune system, different reactions with the immune system, all of them have evidence that they can and do happen. And so the level at which each happens is hard to pin down, because it varies according to pathogen, it varies according to population, types of air pollution exposure, length of air pollution exposure. But I want to reiterate that these two things are so linked that there isn't just one way in which they work together, quote unquote, to create worse respiratory outcomes in human populations, as well as in animal and plant populations. If you want to find a lot of research about the effect of air pollution, respiratory pathogens, there's actually a fair bit on fish and mollusks, which I didn't know until I was prepping for this talk. Okay, so of course, we want to talk about COVID-19 and some different examples that we see. Do we see this playing out during the current pandemic, which is of course due to a respiratory pathogen? This was a study from the journal Science Advances by Wu et al., and they looked at air pollution and COVID-19 mortality across the US. And I really like their title because it's Strengths and Limitations of an Ecological Regression Analysis. So they're noting right from the outset that, hey, this is difficult to do. It's difficult to parse out the effect of air pollution in the presence of all of these confounders on using ecological methods, but they did their best, right? You see on the left here, levels of PM 2.5 being much higher along the eastern side and coasts of the United States, through the Rust Belt and the Steel Belt, and the South being eased as you move west until you hit Los Angeles and Southern California. Of course, Utah, we have higher levels than many other places in the rural West. And then when you look below, you see COVID-19 deaths per 1 million people. And there are lots of different drivers here, right? So if you want to look at mortality, you're going to see a lot more mortality in places like New York City that got hit really bad, really early. And of course, they do also have poor air pollution levels, but they also got hit before we knew a lot about how to go about treating COVID-19. So that's another potential confounder, is that as you look over time, and because air pollution studies tend to be temporal in nature, you're going to have some confounding as epidemics and pandemics progress, because as we learn more, fewer people die, right? So after it hit New York, we found, and during that process, a lot was learned about severity, when to intubate people, when to give steroids and medications to prevent blood clots, which saved a lot of lives. So we have some confounding there. But if you look at places like Arizona, New Mexico, they got hit over the summer right after we knew a lot of this, but they still saw a lot of mortality, especially in areas like the Navajo Nation. That's probably due more to the effects of poverty, of lack of healthcare access, and a variety of modifiers. However, all of that being said, and of course, the authors again acknowledge that there are limitations. They still found higher COVID-19 incidence and mortality associated with long-term exposure to PM 2.5. I think the map on top is PM 2.5 over 17 years. So they're looking at exposure over a good part of the life course. This is a finding that's been confirmed by several other studies in several other countries. Keep checking my time. Okay. Here's another research example. This one is from China. Association between short-term exposure. So the last one was long-term. This is short-term exposure to air pollution and COVID-19 infection. And I thought it was just really striking. So what you're seeing when you look at each of these plots, of course, each one represents a different type of pollutant. And then as you move from left to right across the x-axis, you're seeing a different amount of lag time between a certain pollution level and outcome from infectious diseases, so, or from COVID specifically. So 0 to 7 days, 0 to 14 days, or 0 to 21 days. And you can see that the farther along you get, right, the more time you include, that you still see impacts from air pollution, or correlations, associations, when you're including data as far out as 3 weeks later. And the strongest relationship seems to be with PM 2.5 and PM 10, less so with SO2. NO2 is very strong. Ozone, a little bit different. Carbon monoxide, not quite as strong, but still trending in that same direction. I thought this was really interesting, really quite compelling. So in conclusion here, I think there are 3 main takeaway points that we want to think about in relating ARIs and air pollution. The first is that air pollution exacerbates, predisposes to, and increases the severity of ARIs. It's not just one effect. Air pollution is doing all 3. And through a variety of causal mechanisms, like we've discussed, for which there's an awful lot of evidence. That evidence that both indoor and outdoor air pollution increases risk of ARIs is extensive. It's found in countries around the world. Of course, there can be some publication bias, but historically and currently, there's just an awful lot of evidence that there's a strong relationship. This is, of course, a major public health issue, and one that I think we've become much more aware of because of COVID-19. You see a lot more research being done on the link between air pollution and a variety of bioaerosols, respiratory pathogens. And it's also an issue of environmental and social justice that we need to keep in mind when we want to focus on protecting and providing better health for places that are traditionally underserved. And with that, I think I've reached my half hour, just a minute shy, and I'd love to open it up for discussion. If there's something, further studies that you're aware of, I'd love to hear about them, and if I can answer any questions.
Who has questions?
Seth, this is Jaron Hansen, and if nobody else is going to ask a question, Chantel, can I ask you a question then?
Yes, of course, Jaron.
Thank you, by the way, for putting together this presentation. And I hope I don't embarrass you, but everybody should know that Chantel's getting married in just what, tomorrow, Chantel, the day after tomorrow?
Day after tomorrow, yeah.
It's stressful to be putting together a plenary address as you're also getting ready to get married. So thank you for doing that.
Yeah,
but that was my comment. Here's my question, and that is, and in just a second, you're going to realize that I'm an analytical physical chemist that studies atmospheric chemistry. I'm not a biochemist. I'm not an MD. And so you may need to correct some of the vocabulary I'm about ready to use. Okay. So
go for it. Yeah.
There's my my preface here. Early on, you talked about how PM is known to activate this inflammatory immune response. This is where we think the mechanism comes from, is the origin of the mechanism as to why people get sick when they're exposed to high concentrations of PM. So I've wondered for a long time, we also have medicines that are pretty good at deactivating, if you will, or negating that inflammatory response. Things like taking ibuprofen or naproxen, things like this, do a good job at minimizing that inflammatory response. And we even have new medicines now that are really good at calming what they call it's the cytokine storm that we've been hearing about now, especially involving COVID patients that are, exposed to high concentrations of PM. Is it possible that, let's say that we knew that, UDAC comes out and says, guess what, an aversion's going to settle in this next week. We expect PM concentrations are going to rise. Could we simply say to people, go ahead and drive as much as you want, just go home and take 800 milligrams of ibuprofen, or we're going to have you start taking some of these anti-inflammatory drugs that we know are also going to minimize this cytokine storm, and then everybody's going to be just fine. Could we give drugs to people to minimize the effects of PM?
There's a lot to unpack there. I'm going to think about it one sec. I would say that things like inhaled corticosteroids, in a sense, do just that. So if you are asthmatic and you're taking your inhaled corticosteroids every day, like you're supposed to, then it helps modify or prevent that that outcome. I think there are certainly medical reasons why side effects, interactions that we probably shouldn't just recommend everybody take certain medications in the presence of an air pollution event. But, you know, that's not something I've thought about super long, but, you know, could it have some benefit for some people? Like, potentially. But especially with those medications that block things like cytokine storm, right? Cytokine storm is this last ditch effort by your immune system to just hit what it's facing with everything it's got, and it does tons of cellular damage. And those are fairly intense medications that it's not something we can really use on a population-wide, you know, weeks on end basis if we've got a 2-week inversion. Probably just better to prevent the air pollution.
I agree, Chantel. Yeah, thank you.
Chantel, can I give you backup and also ask a question? So in addition, Jaren, just to add to what you've been saying, you know, inflammation is not always a bad thing. It's like part of the body's healing process, right? And so you don't want to suppress all inflammation, because then you'd be suppressing your body's attempts to heal other things too. But in addition to inflammation, air pollution is known to alter the regulatory immune system and depress the function of macrophages and some regulatory T cells. And so you have this issue of like inflammatory, you know, cytokine release, but then also the issue of the fact that your immune system itself can be hindered by inhalation of PM2.5 and other particles. So it's quite complicated. I think that's what I'm trying to get a hold of here. So Chantel, and I was like thinking about the articles that you had read in preparation for this talk. So many of them focused on PM2.5, but PM2.5 really is just a mixture, right, of particles of a specific size. And so I'm just wondering if if people have looked at, you know, a component analysis of like PM2.5 and how perhaps like some of those particular like compositions might be related to an increased risk for infection. Like, for example, heavy metals in PM2.5 might be mechanistically different than like dust particles, right? So just wondering if you'd seen anything as you were preparing for this talk.
For sure. Great question, Judy. And thanks for the backup and clarification there. I think that those are both really important points. I have not seen a lot of that type of work, that component analysis specific to ARIs, but it could just be that I haven't seen it. Most everything I've seen uses either fixed or personal monitoring to just get PM 2.5 or NO2 levels. Those are the two that I've seen the most in relation to infectious disease outcomes. But if others have seen that, I would totally be open to hearing about those studies. It's just not something I'm as familiar with. But do heavy metals and dust particles influence our immune system and our outcomes differentially? Almost certainly. I think that's a really important point you bring up.
I've got a question for you. If you can go back a couple slides to the lag time slide there. I was trying to wrap my brain around that one. Perfect. So I'm not entirely understanding the vertical axis on this, other than the fact that that bigger numbers, 30 is a lot like Spinal Tap's 11, and so it's got to be worse. I'm noticing that SO2 and ozone seem to be bucking the trend that the other ones are doing. Do you have any more, I realize this isn't your research, but do you have any more insight on kind of understanding and helping some random physicist wrap his brain around this set of charts?
Yes. So and I am pulling this back up so I make sure I'm not lying to you. Okay, yeah, so it's percent change, I just wanted to make sure I was right about this, is the change in cases from COVID-19. And so when you look at the difference between the different pollutants, what you're seeing, 1 week, 2 weeks, 3 weeks out, with PM2.5 levels and how they relate to changes in COVID-19, is you're seeing that that effect, that air pollution exposure seems to have an increasing effect the more time that you look. So, or the longer time window in which you count those COVID-19 cases. So whether it's 1, 2, or a full 3 weeks. And so to me, that message is that the effect of short-term air pollution exposure lasts over time and continues to increase your risk for developing or COVID-19 as time progresses. It's not just within that first week, but it progresses through longer time windows. I think ozone interacts with your lungs and immune system differently. It's also, of course, something that we see more in summer than in winter. SO2, I've also found to be a little more difficult to study personally in these temporal ways. So I always tend to hesitate when looking at SO2 graphs in relation to this stuff, just because the monitoring tends to be set up a little bit differently from the particulates and NO2. And it also tends to be on a different temporal trend than the others. I always tend to see PM2.5, PM10 higher in winter in most places. So there's a lot of difference between the pollutants. I like that they broke out the difference between the pollutants. And it makes sense to me that we'd see more of a trend with things like PM2.5 that are higher coincidentally in winter, especially in China, of course, when this first hit, through, as it progressed throughout the rest of the world. I'm not sure if I made that as clear as mud.
Well, if nothing else, I understand the axes better.
Okay, good.
Chantel, Tabitha, Benny has a question, and then there are a couple in the chat too. So.
Oh, okay, great.
Hi, Chantel. It's great to see you again. We haven't seen each other.
You too, Tabitha. It's been a long time.
Congratulations on your wedding. I'm so excited for you. That's great news. I think I knew you when you got engaged originally, so this is great to hear that you've come around full circle. So this is a wonderful talk. I really enjoyed it. We've also here at the U been trying to sort of get at this very difficult sort of question. Early on, we gave up in some ways. We did find similar pollution patterns, and SO2 and ozone interact with other types of emissions, and that's why you see these patterns that are different. They sort of eat each other up compared to the first 4 emissions. So we also found a similar pattern to that. But my question about the work you presented today, we're seeing now more research coming out that's suggesting that with increasing pollution, we might actually be finding a transmission mechanism, not just COVID-19, but other forms of diseases in urban areas. Infectious disease, etc. What is your sort of thoughts on that? And do you think that that is a growing vulnerability for cities, this notion that disease is being spread through air pollution?
Yeah, I think lots of great points. It's really interesting. I'd love to hear more about what you guys found, and I hope to hear more about that. Um, it is a growing problem. Absolutely. We are also seeing this with influenza, with tuberculosis, the same kind of increase in both severity in outcomes and also the R naught, right? The basic reproductive number that we're also familiar with now increases with increasing PM exposure in particular. And so if you it's certainly a problem across kind of the respiratory and infectious world, though of course it varies by pathogen. Absolutely. And I'm having trouble pulling up the chat.
I can just ask, I'll just read those
Yeah.
questions to you. It's too many things to handle, I think, to do all of it at once. So the first question says, what kinds of solutions have agencies, nonprofits, research organizations, et cetera, found for reducing the air quality component of underserved populations' poor health outcomes, like maybe replacing biomass stoves or wood stoves?
Yeah, great question, and one that I think could probably be answered better by other people on the call than me, but or part of this conference than me. But of course, replacing stoves. Heard a lot about increasing ventilation, number of windows, improving home filtration systems, helping people understand air quality as something important to monitor and track. Of course, that definitely varies around the world and among different populations, how closely that's tracked, how transparent governments are about it, whether they be city, state, or national. So there's a lot of different things being tried in impoverished areas, whether urban, rural, or underserved nations. And there's a lot that we have left to do is a simple answer to that, but it's a huge, obviously a huge source of work for air pollution researchers and health promotion advocates around the world.
Great, thanks. And then the other question is, how can an increase in asthma cases and the decrease in air pollution over the past 20 years be reconciled?
Yeah, that's a big one. That's a big one. So there are a lot of things that contribute to asthma as an outcome. So we know air pollution is an issue, but of course, respiratory infections is also exposure to dust mites and other indoor allergens we know is a contributor to the development of asthma. You know, another thing we've seen, we know maternal smoking contributes to asthma development early in childhood. And as we've seen smoking rates fall, we do see, you know, variations in levels of asthma in different populations. So I would say, for one, air pollution is far from being the only contributor causal part of the etiology of asthma. For two, we have, of course, increases in diagnosis of asthma, different types of asthma. Third, you know, that decrease in air pollution isn't the same everywhere. Some places have seen increases. Some, you know, it's variable, and as you see, you know, a widening of in the income gap. We see major problems with urban housing increasing, and how well, you know, housing is upkept. Children are being exposed to all kinds of things. So I would say that asthma is a very complex problem, and seeing one etiological factor decrease doesn't necessarily mean we're going to see a resulting decrease across the population just because it's so complex.
Great, thank you. We're out of time. Thanks so much, Chantel, for speaking to us and for answering so many questions.
Oh, you're very welcome. It was a pleasure.
Great. We're glad to have you here. It's time now for